Lovely flying weather, isn't it? Nice time to be out in the middle of a big, dark, damp nowhere. Even the old hands aren't happy about this one. There are so many stations transmitting, and the air is so filled with electrical disturbances from the storm that even when the pilot tunes in the right range, he can't distinguish its identifying signal because of the static. There are a couple of new instruments on the panel which take the guesswork out of radio navigation. They are the track line indicator on the left and the radio magnetic indicator. Unwavering as a bird dog on a scent, the radio magnetic indicator's double needle points directly at the omni-range station to which we attune. All the pilot does is watch the vertical needle of the track line indicator. If he keeps it centered, he'll fly a track directly to the station. Hit it on the nose. Nice, huh? No static, no ear-splitting beam signals. Just fly the needle, and Omni will get you back to operations right on your ETA. Let's find out what makes this amazing new system of navigation work. If you see something like this being erected, you'll know Omni is soon to be in operation. For this is what a VOR station looks like. This is the hub from which spokes run out in all directions, giving you an infinite number of legs which will form an interlocking pattern blanketing the country. Instead of searching for a leg to intersect, as we used to do, you'll simply take the leg, known in Omni parlance as a radial, which intersects you, then fly that radial to the station. Actually, what happens is this. Each omni-range station is assigned a certain frequency. In this case, 114.3 megacycles. Knowing that, the pilot simply tunes in the correct frequency on his frequency selector, sets in the desired track on our track indicator dial, and flies the needle to the station. If the pilot wants to go past the station on the same track, he will know when he's passing over the station by the fluctuation of the ambiguity meter and vertical cross pointer. He then flies out the reciprocal leg merely by keeping the vertical cross pointer centered. All omni-range signals are generated from the station and are transmitted along line of sight. At an altitude of 1,000 feet, an Omni signal can be picked up by a plane at a distance of 50 miles. And at 5,000 feet, for about 100 miles. Taking a look at the situation from an exaggerated viewpoint, we find that between stations on the same frequency, this line of sight practically eliminates interference as long as an aircraft cannot, figuratively speaking, see both stations at the same time. In this more natural perspective, we observe that very high-frequency omni-range stations are being erected at intervals of from 90 to 100 miles. Only at intervals of 500 miles or more will the same frequency be repeated. Intermediate stations will each operate on a different frequency. It is possible that at high altitude, a pilot may get interference from two stations on the same frequency. To eliminate this condition, the pilot should retune his receiver to a station on his track which is nearer to him. This will, in effect, put the plane in a position where, in a radio sense, the pilot can see only the station he desires to use. Therefore, with stations placed at 100-mile intervals, a plane flying as low as 1,000 feet will never be out of range of an Omni station. Leaving an Omni station, for example, the receiver in the plane is tuned to the frequency of that station. As the pilot approaches the extremity of the leg, he'll turn the selector to the frequency of the next station. Fly into and out from that station until he is close enough to the third station to pick up its signal. This frequency change procedure will be repeated for each successive station until the plane has reached its destination. Each VOR station is assigned a frequency between 112 and 118 megacycles. Signals transmitted in this static-free band are generated at the station and received by airborne equipment, which presents them visually. Let's take a closer look at the new instruments a pilot will have: the track indicator, the radiomagnetic indicator, and the channel selector. Say, for example, that a pilot wants to go to Indianapolis. First, he finds in the facilities chart that its omnifrequency is 116.3. He then sets that figure in on the channel selector, the 116 with the larger knob, the 0.3 with the smaller knob. That's all he does. No tuning, because the receiver is crystal controlled. Once the channel is set up, that's it. The RMI gives two valuable pieces of information: magnetic heading of the aircraft, read under the lubber line, and the direction from the aircraft to the Omni station, indicated by the double needle. Reading the pointer of the double needle against the compass card gives you the magnetic bearing to the station. Regardless of the aircraft's heading, the RMI always points toward the Omni station. The other needle may be used as an ADF indicator or for another Omni receiver if you happen to have more than one aboard. In this instance, the pilot makes a normal into-the-needle turn. Both the needle and the dial rotate until the heading of 290 degrees and the needle are both under the lubber line at the top of the indicator. Now that the plane is headed toward the station, the pilot wants to hold his track. This is where the track indicator comes into the scheme. According to the RMI, the heading along the radial to the station is 290 degrees. Therefore, the pilot turns the setting knob until 290 degrees shows on the track dial. If he's on that track, the vertical cross pointer will be centered. The ambiguity meter will read 2, indicating that the heading the plane should fly to reach the station is 290 degrees. If the plane is off track to the left, the vertical cross pointer will be off to the right, indicating that an into-the-needle turn is necessary to get back on the radial. If the plane is off to the right, the converse is true. An into-the-needle left turn is used to get the plane back on track. Simply by keeping the vertical cross pointer centered, the pilot flies a track directly to the station. Remember, the vertical cross pointer shows displacement from the Omni radial and has no relation to aircraft heading. These two instruments will give you all the information you'll need to fly Omni. The RMI gives you the bearing, and the track indicator enables you to hold a desired track. In some commercial and private planes, the track indicator may be divided into two separate instruments: the track selector and ambiguity meter, and the track deviation indicator. Again, the procedure is the same. Tune in the station, turn the track selector knob until the ambiguity needle points at 2, and the vertical cross pointer is centered. Then read the magnetic track to the station and make your heading jibe with the track selected. Here, in another example of available equipment, the track indicator is broken into 3 separate components: the track selector, the ambiguity meter, and the track deviation indicator. Again, the steps are the same, although in this case, tuning is done manually instead of by crystal control tuning as in previous examples. Turn the track selector knob until the vertical cross pointer is centered and the ambiguity meter reads 2. Just fly the track indicated. It's as simple as that. Now let's take the Omni instruments apart to get a clearer picture. In the RMI, there's a compass card rotated by a flux gate or gyrosyn compass. Under the lubber line, the aircraft heading is always read with respect to magnetic north. Now for the Omni needle. It always points to the station. The track necessary to get there appears on the compass card under the point of the needle. In this case, 300 degrees. Notice that the bearing information given is always from the aircraft to the station. Third component of the RMI is an ADF needle, which, if desired, can be tuned to a standard broadcast station, much the same way as the present ADF or radio compass indicator with which you're familiar. The track indicator is equally simple in its visual presentation. Although several operations have been combined within this one instrument, first move is to set the desired track on the dial. The RMI pointed out that the bearing to the station is 300 degrees. So, 300 degrees is set in the window by turning the track selector knob. Next, the heading needle. This always indicates the heading of the aircraft with respect to the selected track. If, for example, a track of 300 degrees is set in the window and a heading of 300 degrees is maintained, the heading needle will be vertical and will read 0. If the heading is changed, the needle will show how much and in which direction. In other words, once a track has been set up, the heading needle shows change of heading from that track. As we'll see in a moment, it's also used in conjunction with the vertical cross pointer. The cross pointer, or deviation indicator, includes a horizontal glide slope indicator used with the ILS, which we'll see later, and a track deviation indicator, or vertical cross pointer, which shows whether the aircraft is on track or off to the right or left. Now let's watch the track deviation indicator and the heading needle operating as a team. Say the bearing to an Omni station is 300 degrees and an aircraft at this moment is dead on that radial. The track deviation indicator will be centered because the plane is neither to the right nor the left of the radial. However, the plane's heading is 270 degrees. The heading needle clearly indicates that the aircraft is not headed along its desired track. It is actually heading 30 degrees left of the desired track. If the plane continues to fly the 270-degree heading, it will leave the 300-degree radial, and as it does so, the track deviation indicator will move right of center. This tells the pilot he must make a right turn to get back where he belongs. As he turns through a 300-degree heading, paralleling the correct track, the heading needle is straight up, centered, and the vertical cross pointer holds to the right, indicating the plane is still left of the track. He continues his turn until the end of the heading needle is directly under the vertical cross pointer. This indicates that he is approaching his track from the left. He holds this heading until, as he approaches the 300-degree radial, the vertical cross pointer begins to move toward center. The pilot now turns left to bring the heading needle back to center as well. With both centered, he knows he's on the correct track and radial to the station. We left the track indicator all assembled except for two small items, the flag alarm indicators and the ambiguity meter. The flags simply tell you if you have signal enough to use. If you don't see the flag, everything is okay. If you do see the flag, disregard what the instrument says because you're either too far away from the station or the signal has failed. The function of the ambiguity meter is just as simple. If you're flying a radial which will lead you to an Omni station, this savvy little gadget lets you know it by having 2 pop up in its window. If you're flying a radial away from the station, it shows from. Simple but most useful information. As long as you are flying a radial which will lead you to an Omni station, 2 will be staring at you from the ambiguity meter in the track indicator. And you will know when you're passing over the station, since the ambiguity meter will flip up and down, finally settling on from. It will continue to show from as you move on track away from the station. How about our boys up there flying through the storm? Remember them? Yeah, still buzzing along, homing in on the Miami Omni range. How do they know that? It's a breeze. The range identifies itself in one of 2 ways. By voice, "This is Miami Omni range. This is Miami Omni range." Or by code. There's no question about it. The range has identified itself. The ambiguity meter says they're going toward the station. The track deviation pointer is centered, but hey, look at that heading needle. 15 degrees off. We'd better check the RMI. Heading, 5 degrees. Bearing to Omni station, 20 degrees. Selected track is 20. That's correct. But the plane is heading 15 degrees off that track. What happened? Well, the answer is obvious. The pilot is keeping the vertical cross pointer centered. In other words, he's making good a track, not a heading. And in this strong crosswind, to keep the cross pointer centered, the pilot must fly at a crab angle. As long as the vertical cross pointer is centered, the omnibeam will lead the pilot right to the station. Say, how are the boys doing? Well, they're tuned to the Macon Omni station, which is leading them in until they're within range of the Atlanta ILS. This very same track indicator is used to fly the ILS for instrument approach. A very high frequency band ranging from 108 to 112 megacycles has been assigned to provide channels for the localizer transmitter, while the glide slope operates on frequencies in the UHF band. The co-pilot checks the facilities chart for ILS frequency.
ILS frequency 109.9. Runway bearing 088.
Okay. Seems like you're right of track. Your heading needle shows you that you will intersect your track by holding your present heading. Just keep the heading needle under the vertical cross pointer as it moves toward the center, and it will bring you right on track, which is along the bearing of the ILS runway. As an added safety measure, GCA will monitor their approach.
This is GCA Final Approach Controller monitoring your ILS approach. Do not acknowledge these instructions. 8086, you are now 6.5 miles from touchdown, right on center line, now approaching glide slope. 8086, you are now 2.5 miles from touchdown, you're on glide slope, 40 feet off of center line. 8086, you are now 1 mile from touchdown. You are 20 feet high, right on center line. 8086, you are now 1/2 mile from touchdown, right on glide slope, right on center line. 8086, you are over touchdown, take over visually.
Thus we have seen how Omni and its running mates, the ILS and GCA, have brought the aircraft in through the storm to hit its ETA right on the nose.